Good afternoon. My name is Samantha Decker, and this is my presentation for our Advanced Concepts presentation number 3. This week's presentation, I'm going to be talking about the Michaelis-Menten equation. The Michaelis-Menten equation describes the kinetics of numerous enzymes. In this video, I am going to walk you through how the Michaelis-Menten equation is derived from given starting materials, and I will also define Km and Bmax and explain how those things fit into the equation. So first things first, I just want to say that I'm going to try to first talk about the equation, and then write and just kind of go back and forth. So hopefully that works out well. I'll also just show you off the bat that I am indeed using a blank piece of paper, so no questions about that. So let's get started. We start with our enzyme, which is illustrated using a capital E, and our enzyme reacts with our substrate, capital S. In the first step, E and S join to form the enzyme substrate complex, which is also referred to as the Michaelis complex. Already messed up, so I am going on to the next paper. So this is our first reaction. Note the double arrows in the first reaction. This means that the reaction can proceed in both forward and backward directions. In the second step, the enzyme substrate complex breaks down, giving us the enzyme and product. This is the second reaction. Note that this reaction only goes in the forward direction. The backward reaction is negligible at this stage. Next, we will assign variables for the rate constants of these reactions. K1 for the forward part of reaction 1, K-1 for the backward part of reaction 1, and K2 for the forward part of reaction 2. To prove that these steps are correct, we need to add the reactions together, and we'll see that the two ES complexes and two enzymes cancel each other out. This leaves us with our net reaction, the substrate going to product. So let's start solving. We know approximately that the creation of the ES complex is equal to the sum of all reactions decreasing its concentration. So reaction K1, which forms ES, minus K-1, which consumes ES, minus K2, which too consumes ES, is subsequently all equal to 0. This is written as the instantaneous rate of change for ES over dt equal to K1 times concentration E times concentration S minus K-1 times ES minus K2 times ES. And this all equals 0. Let me just draw that out for you. Get a good look at it there. These expressions like K1 times E times S are similar to our methods for initial rates, when reaction rate is solely determinant on the concentration of the reactants, in this case E and S. It is difficult to determine the value of unbound E, so to solve for this we use E total equals E of the unbound enzyme plus ES, the bounded enzyme. Another way of writing this can also be E equals E total minus ES. I'll show you that now. So like I said, this is just another way of writing that. Then we just have to subtract ES from both sides to solve for E. Next, we substitute D concentration ES over DT into our prior equation for E. This gives us D concentration ES over DT equals K1 ET minus ES times S minus K1 times ES minus K2 times ES. Let me draw that out for you now. Quite long, sorry about that. Then, if we distribute the K1 and S, we are left with K1 times ET times S minus K1 times ES minus K1 times ES minus K2 times ES. So once again, this is what the equation looks like after we distribute the K1 and S. The goal here is to find ES concentration, so we must move all of the ES to one side of the equation to be able to accomplish this. So that means we need to factor out ES from this equation. So next, that's what I'm going to do. Factoring out ES will give us this. Next, we'll just need to divide by ES. And that will give us what I'm writing now. Sorry, I'm just double checking my work here. And I'm getting to the end of the page. So after we divide for ES, we are given this. We then need to multiply both the numerator and the denominator by 1 over K1. And that gives us this. Like I said, this is what we get after we multiply the numerator and the denominator by 1 over K1, and we're still trying to isolate for the concentration of the enzyme substrate complex here. So next, the instantaneous rate of change for product P, D, concentration P, is a function of its reactants, and there is only one reactant for equation 2. Like we said, equation 2 only went in the forward direction. So that gives us D concentration P over dt is equal to K2 ES. Since we now have an equation for ES, we can substitute this in and we are left with the Michaelis-Menten equation, which is what we've been trying to derive this whole time. So velocity, V, in the Michaelis-Menten equation is another way to explain the reaction rate, or dP over dt. So this part here, dP over dt, we can actually just fill in as V, or velocity, which is, part of the Michaelis-Menten equation. So now we have V is equal to dP over dt equals Kcat times enzyme total times S over K plus Km. So not to get confused by all of these new additions to the equation, Kcat is just a different name for K2. So Kcat is the reaction constant, and it's actually the turnover number. The turnover number is the number which is the max number of substrate molecules that an enzyme can actually convert to products, so like a threshold. And this maximum rate at which this occurs is known as Vmax. So filling in for Vmax gives us our final Michaelis-Menten equation. Also, Km is the Michaelis-Menten constant, indicating the concentration of substrate when reaction velocity is half the maximum. So Km is just half of the Vmax. I know that was a lot, but thank you so much for bearing with me, and have a great day.